Good morning, guys. Some students requested maybe a recap video on the chromatography assignment from last week, so I figured I would connect it to the IMF activity that you did as a discussion yesterday and hopefully connect all the dots and show you why these are all in the same unit. So first, if you had, everyone had to do number one. So I put down the electronegativity. So we have on this guy, we have a carbon, we have oxygen, hydrogen, and hydrogen. And so based off the difference in electronegativities, I know that this bond here is polar covalent, meaning they're sharing unequally, and these are nonpolar, meaning they're sharing equally. Because there's a polar bond on one side and it's not canceled out in this molecule, we do have a dipole moment with a partial positive section down here and a partial negative section up here, which means the overall molecule is polar. So if I clone that molecule, here's kind of what I want you to see, and I'm going to actually focus on this center one. This is the nonpolar section. So this nonpolar section is capable of interacting with the nonpolar section of its clone. Whereas, let's erase that. Nope, that's a highlighter. Good try, Butler. Or not, we just won't erase it. Whereas the partial negative oxygen right here is capable of interacting, I'll do this guy actually, partial negative oxygen is capable of interacting with this partial positive section. So that could be the carbon or the hydrogens through dipole-dipole. So we have two things happening, London dispersion. One, because everything has London dispersion, but also because the nonpolar part can interact with the nonpolar part right here. And then we also have the dipole-dipole interaction happening between the partial negative and the partial positive. All right, last name A through D. I'll try to go through these quickly. We have all carbon bonded to hydrogen. This is called methane. It's a CHHH. So that's methane, and we have nonpolar covalent bonds, all shared equally. So because this molecule is made of all nonpolar bonds, it means there's no dipole moment. They're sharing equally, so the molecule is nonpolar. If we clone a nonpolar molecule, we know that for a hot second, maybe all the electrons move to this side of the molecule, making it slightly partially negative, which causes the molecules near it maybe to do something similar, so partial positive. So that would make this partial positive, this partial negative. But that happens for such a hot second that we don't even write it down. So what I wrote in yellow is not something you should write on your page, but that attraction due to momentary dipoles is called London dispersion. London dispersion is the weakest force. Methane at room temperature is a gas because it's not very attracted to clones of itself. It's a gas at room temperature. All right, last name E to O. So you had your carbon, you had oxygen and hydrogen. So we said that this bond here was nonpolar, this one is polar, this one's polar, and this one is polar. Lots of dipoles happening here. So we have one dipole moment kind of pulling electrons up towards this oxygen. And then we have a big dipole. Notice it's a thicker arrow happening here towards this oxygen and kind of this way. So really overall, I would say that there's a big dipole kind of pointing in this direction. And then we have a smaller dipole pulling up. So polar molecule. When we clone that, that oxygen with the smaller dipole pulling up, like this one, is capable of interacting through dipole-dipole, so that partial negative interacting with a partial positive. But we also have dipole-dipole on steroids. When we have an H directly bonded to an F or N, that really partial positive hydrogen can be attracted to that really partial negative oxygen of the other molecule. Notice I'm only doing the dipole-dipole with the special hydrogen. This guy right here, that special hydrogen with the special oxygen. It's not with the extra oxygen. It's not with the extra hydrogen. The special hydrogen with the special oxygen, special hydrogen, special oxygen. That's hydrogen bonding forces. Okay, we also have London dispersion that happens everywhere. All right, this one I call the caterpillar, like there's caterpillar's head, his nose, his body. But if you had last name P to Z, so we have this whole thing is nonpolar, right? Nonpolar carbon to hydrogen, nonpolar carbon to carbon, a little polar there, and then very polar right here. So if we draw our dipole arrows, I say that this molecule has a polar head, right? Over here, this part is polar. If I drew the general direction, we'd be kind of pointing, oops, wrong thing. We'd be pointing this way just because of that bent shape. And then over here on this side, we have all nonpolar. So I say that this molecule has a polar head and a nonpolar tail. Nonpolar meaning this section, polar meaning this section. So when I clone this guy, the special hydrogen on one caterpillar can attract the special oxygen on the other caterpillar through hydrogen bonding. So not these hydrogens, not that hydrogen, that one, those cannot do hydrogen bonding. Just this special one, okay, can be attracted, or this special one can be attracted to an oxygen. And then this whole tail is able to do London dispersion with this whole tail. So we have basically both things happening, opportunity to hydrogen bond and then London dispersion on this long tail. So let's add polar water, H2O, with this nonpolar and polar beast. So notice, because this part is capable of hydrogen bonding, it is going to be very attracted to the special hydrogen in water, and it is capable of doing hydrogen bonding forces. So this guy can attract an oxygen, or the oxygen can attract a hydrogen, doesn't really matter. But notice I'm not attracting any of this tail. And then we know that the tail part is attracted to the tail part through London dispersion. We also know water is attracted to hydrogen bonding. So the head of this caterpillar is capable of hydrogen bonding with water, but the tail really just does London dispersion with itself. And then the last one was water with this big non-polar molecule. I know it's non-polar because it just has carbon to carbon and carbon to hydrogen bonds. A molecule made of all non-polar bonds is non-polar. So notice water, hydrogen bonding with itself. The big old organic molecule of carbons, London dispersion with itself, a little bit of London dispersion with water just because everything has London dispersion. But notice there's not a whole lot of interaction happening between the water and this big nonpolar molecule. That's going to help us relate to chromatography. So there is a big idea in science, it's like dissolves like. So what I mean by that is if something is polar, like water, it will dissolve with, or it will do the dissolving of other polar things. Nonpolar will dissolve nonpolar things. But typically, something that is polar will not dissolve something that's nonpolar. So when we were talking about H2O with that C3H8 molecule in the last slide, those were not really interacting with each other much because we had a polar molecule and a nonpolar molecule. There were not a lot of intermolecular between those molecules interactions happening. So if I want to do something like dissolving, it's not likely. Think about oil and water. Oil is very nonpolar, water is very polar, and the oil doesn't really mix well with the water. That's the idea that we can get from different molecules interacting. Two things capable of hydrogen bonding are going to interact and dissolve better in each other than two things that are not capable, or one thing that's capable of hydrogen bonding and something that's not capable in hydrogen bonding. So how does that relate to chromatography? Let's look. So in chromatography, we take a piece of filter paper and we draw a pencil line, okay? And then I'm gonna put some different ink. So actually, let's say I take a black Sharpie and I put a dot. I take a black Crayola marker and put a dot, and take a black Flair pen and put a dot. Okay, I'm ultimately going to lower that thing into a beaker filled with some sort of solvent. What happens is, let's pretend that this is in the solvent, so the solvent layer is kind of touching right here. What's going to happen is the solvent is going to begin to rise, and it's going to take those dots with it. Sharpies are made of multiple different colored dyes, and so what ultimately might happen is that we might see kind of a black streak happening, and then maybe we have like a purpley streak happening, and then maybe we have like a yellowish streak happening. As this dye goes up, it's traveling with as the solvent rises up the chromatography paper or the filter paper, we start to see the colors forming, okay? Whereas Crayola markers tend to have like a red color dye and then this kind of greenish, yellowy color. And then my black Flair pen actually just has one color dye and it kind of is in this region. It kind of smears a little. Okay, so what happens is that solvent rise. My question is, why does this line have to be made in pencil, that line right there? Well, if we know that markers or other things are made of dye that respond to the solvent, we don't want if I used a pen, for example, to draw this line, I don't want the pen color to start bleeding up the page as well. So a pencil will just kind of stay there as a marking for us. In the simulation, the solvent, so the liquid used was salt water, and it's very polar. One, because we know water is very polar, and then when you throw ions in there as well, that makes it even essentially more attracted to things with partial charges. So it's very attracted to polar compounds. So what's happening is I have this polar solvent, and it's rising. You can see it stopped rising up here. And I want to know which color dye, blue or yellow, is most polar. Well, we know like dissolves like. So the dye that traveled the farthest with the polar solvent is going to be the most polar. So the blue traveled the farthest, which makes it the most polar because the solvent was polar and this traveled the farthest. The least polar then would be the yellow color dye because it did not travel as far, meaning it's not as attracted to the polar dye. All right, if you and I both did this lab, how do you think the solvent would go the same distance? And how about the dyes? And why do we have to calculate that RF value? So, a couple of things. What if I put mine in and I let it go for 15 minutes? And you did the same thing, but you only let yours go for 7 minutes. What I will notice is that my solvent travels a farther distance than yours, and yours travels less because you let it run for less time. Is that bad? Well, it depends, right? There's not a lot of comparing that can happen if we don't have the same amount of time, same distance that the solvent traveled, but that's why we can calculate our F value. So if I take that this is the solvent front, and then I take the distance, let's say red, for example, that red traveled. So I take red over how far the solvent traveled. That's going to give me an RF value for that red dot. And if you do the same, how far did your red travel compared to the solvent front? That should give you an RF value that's very similar to mine, even though our chromatography papers look very different, because it's all about this ratio. So we are able to compare one to the other by calculating these RF values, even if our samples look very, very different. I know we did not do the Dr. Hobbs lab, but the idea of the Dr. Hobbs lab is we were analyzing a note that was written and 3 pens for people who worked in the lab to see what pen was used to write this note, this murder note. And so what we can do is if I put some ink from the murder note and then I have some unknowns, what we should see is if I saw something like this, that would tell me that whoever uses this pen was the person who wrote the murder note. So you can kind of match it up versus if we saw a pen that separated into maybe 2 colors or 3 colors, things like that. And last but not least, instead of using water or the salt water, what if we use chloroform, CHCl3, and it's less polar? Here's why it's less polar. Water is very polar because it has the ability to hydrogen bond on this side of the molecule, right? H to another O. And it has the ability to hydrogen bond on this side of the molecule. And don't forget about the salt in there. So I also have these positive and negative ions floating around, which like to respond with temporary or dipoles and things like that. Anyways, what if I use something like this? CHCl3. Here's it kind of drawn in 3D. We see a tetrahedral geometry. We know it's less polar, but let me show you why it's less polar. If I draw it flat, do you see how this bond and this bond, even though they're polar, they cancel? This bond is non-polar, and it's countered with this very polar bond over here. So if I were to draw in my dipole, it would look something like this, right? Because these guys cancel, and so we just have this one kind of outweighed polar bond. So we get a small partial negative. This whole kind of chunk is partial positive, or you could think of it this way. This guy's partial positive. These guys had canceled each other, right? Or sorry, this guy's partial negative, and then this whole kind of piece is partial positive. Either way, it's less polar. So what do you think would happen? Well, that I would suspect that the blue dye, which was polar and traveled the farthest, would travel less far, right? And maybe that other color dye, I think it was yellow, would travel a little more. And we can do the same if I did a non-polar dye. If I did something with only carbon and hydrogen bonds that was non-polar, we would expect a non-polar dye, like the yellow, to travel farther, and then the blue dye to stay closer to where it started, travel less far. So hopefully that helps wrap up IMF and chromatography for you. Sorry it ran a little long, but I'm hoping it was informative.